So welcome to lecture 38. This is going to be on propagation delay of digital circuits. We started digital circuits last time. Just some announcements to begin with. So homework number 11 you know is online. That's due this coming Friday. That's your last homework assignment. So after that you won't get another one. But you will still have your lab number 6 to work on. That of course has been online for a while. That's due the next Friday. So the last day of the RRR week. And you turned in one checkpoint for this week in the first 2 days of this week, and next week you have another checkpoint that's due, the second checkpoint, which is a breadboard circuit of your design that only really needs to meet 2 of the requirements on that, or if even, I suppose. Just get something breadboarded so we know that you're working on it. Again, these checkpoints are mainly to make sure that you're not caught at the last minute trying to finish this lab. This is a much longer and bigger lab. Some people have already been trying to breadboard their circuit, and they are running into issues that we know will happen in the practical circuit. So there are things that you'll have to be concerned about, like feedback, I guess positive feedback that can cause oscillations and that sort of thing. So if you run into trouble, don't hesitate to go to office hours and contact your TA, go to lab and that sort of thing. This lab is designed to have you run into problems, practical problems that you will learn about and learn how to solve. So I guess those are the course announcements. We're near the end here. So we've got after this one more lecture, and so in the next lecture, since we won't have any more lectures after that, I will go through a final exam information sheet. I'll post some sample final exams for you to look at as well, just like we did for the midterm. The final exam, again, is going to probably be something that will involve a little more design than the previous final exam it had, but you did okay with that on the midterm, and so I think after these 2 projects, the lab projects 5 and 6, you'll probably do even better on the final exam. But we'll talk more about that next time. Also, next time I'm going to leave some time for course evaluations, so maybe be prepared for that. I guess if you don't know how to do those, which I suspect there's probably no one in that camp right now, but anyway, you can go to this website right here that will give you at least how to do it, and also, I guess, best practices as well. These are videos made by the Eta Kappa Nu folks. Please do the course evaluations. You don't have to do it next time, but at some point before the semester ends, please do them, because it's a good way to help the next generation of students that are trying to decide what course to take, decide whether they want to take this course or not. I guess with that, I will ask any questions about anything in the course, logistics. Okay. So let's go ahead with the lecture topics, and we're up to propagation delay. So last time we looked at a CMOS inverter voltage transfer characteristic. Now that was really not much different than what you'd already done as far as looking at a voltage transfer characteristic for an op-amp. You did that in a lab, in a previous lab. And so this is the same thing, except instead of an op-amp, we're using a much simpler circuit. We're using something that has only 2 transistors. We were using an inverter, basically. Whereas an op-amp will have something like it, at least the ones you're using will have 20 to 40 transistors, something like that. And so now we're considering propagation delay. And so this is the last thing we looked at here on the right side. We looked at a cascade of 2 inverters here. And I guess one thing I didn't say last time was identify this device that I've drawn here. So I've got this device here that kind of looks like a transistor that we've seen before, but not quite. What this is the digital way to draw a PMOS transistor. Okay, so instead of drawing the arrow coming down there, which shows which direction the current is coming there, in digital often they will just put a little dot or a little bubble there that signifies an inversion. And so they think of NMOS transistors as non-inverting and PMOS transistors as inverting. And so it sort of is that way, right? PMOSs are kind of the opposite of NMOS there. So all this really means it's a PMOS transistor. And so you're stacking a PMOS transistor on top of an NMOS transistor. You're tying both inputs together, so both service inputs. And then you're taking the output between the 2 of them. And that then can drive a second stage here. And the thing in digital circuits that we're always concerned about, you're concerned about the clock rate of your circuit. You're looking for 2 gigahertz or 3 gigahertz or 4 gigahertz, whatever you have these days in your CPUs on your computer or your phone. And so that speed is one of the most important things to talk about for digital circuits. And so in the end, the way that we measure speed is through propagation delay. And so that's sort of the delay that you get when you put an input signal at the input. You assume that input signal is rising at a finite rate. So you start everything at the 50% point of that input signal. That's not to say that it stays at 50% the whole time. It will rise. So when you actually do an analysis to try to determine how long it takes the output to respond, which is the propagation delay time, usually you don't figure a half of the voltage here. You go ahead and use the top voltage, whatever the V output high is in the end to do that. And you'll see us do that in just a bit here. But right now, you're looking for this 50% point, and you want to measure the time it takes to go from the 50% rise point at the input to the 50% fall point at the output. Right? At the output, you're trying to go from a high to a low now. And what that means is the NMOS transistor is working to suck charge off of this capacitor that you have at that node. So this is what we ended up with. We defined propagation delay. We defined it a high to low propagation delay, a low to high propagation delay. They're not always the same. It depends on the design of this circuit here. But if you design it such that the PMOS transistor is as strong as the NMOS transistor, you'll do that by sizing their W/L ratios correctly. Then you will have a very symmetric signal here, and TPHL and TPLH would be the same. But whether they're the same or not, propagation delay is defined as the average between TPLH and TPHL. So these two divided by 2 for any given inverter circuit. And also for other types of circuits, NAND gates and NOR gates, that are really more complicated versions of this inverter here. They just use more transistors up here and more transistors down here. And so we covered this last time, and the last thing we were doing was wanting to understand how to determine what this delay is. What is that delay? So to do that, we have to understand both how strong the transistor can pull current off of a capacitor, or push current or push charge onto the capacitor. But at the same time, we're looking at how much capacitance is there that you have to put a charge onto and off. The lower that capacitance, the faster you can charge it up and down, and so the faster your circuit. And so what is the capacitance that we worry about? Well, the last thing we did was look at the cross-section of a CMOS inverter. So this is the NMOS device, that's the PMOS device. You can see the PMOS transistors are in an N well. The NMOS devices are in a P substrate. This P substrate is tied to ground, or at least to your lowest voltage. I can go ahead and put ground right here. The N well is tied to your highest voltage. And you know the reasons for this from our physics discussions. You want to make sure that you get no diodes turning off and on, right, between this N and P, etc., throughout this here. So the N needs to be at a higher voltage than the P in order to keep that diode off between these wells here. And so you can see the hookup that I'm showing here. This is the input to that inverter. You can sort of see that this is exactly what is shown up to the right here. And this is the output from this metal piece here. This is ground. This is VDD going from the PMOS device, and ground from the NMOS device source. And so in this picture, and if you want to learn more about this, how this is fabricated, and more about the cross-section, you can take ee143, right? So this is some incentive here to take ee143. You take that class, you'll understand all of what I'm showing right here. But right now, what I'm showing this for is to, one, show you what it looks like, but second, to take a look at the capacitors that we're worried about. And so you already know about these capacitors to some extent. You know that you have, say, a CDB, a drain to bulk capacitance going from the drain here to the bulk. And so I can draw that in here. Do that in green. So I have a capacitor here. That's basically the CDB of my N-type device. I have a similar capacitor, CDB, on this side of a P-type device. I'll do this, CDB-N, CDB-P right there. I also have even capacitance here But this capacitance doesn't matter because you'll see one side of it is ground, the other side of it is also ground. And so that capacitance really isn't there. And I could do the same thing with this one. This one here, this one capacitance is actually going to VDD. And this part is also up to VDD, so I have no voltage drop across that. That capacitance really isn't there. I have gate capacitance. That's what we ended up talking about. We make an inversion layer here. And so I got a capacitance between the gate and my substrate. And oftentimes what you do is split that into two capacitors. So you have one capacitor here that is, say, the gate to source capacitance for the N-type device. You have another capacitor here that is the gate to drain capacitance for the N-type device. And those capacitors, you can see in this case, you could sort of split them in half. You could say half of the total overlap capacitance goes to CGSN, half to CGDN. That's an approximation, and the reason why it's not the same as what we did with analog circuits. In analog circuits, we had a saturated device, but this device now is no longer just sitting in saturation. It's going between off to linear to saturation and back and forth there. So we can't really say that it's 2/3 WL-Cox, which was the capacitance we used for CGS before for analog circuits. We're now going to approximate it as 1/2 of all of that stuff there. And I've got the same capacitors here. And I've got also the CG capacitor. So that would be CGSP. And this one right here would be CGS or CGDP. Okay? But a lot of these capacitors are familiar to you. They just don't take on exactly the same values. And so this is it looking from a physics picture. Looking at it from a schematic picture, which is probably easier to look at. I could take this schematic of this cascade of two CMOS inverters and I could start adding capacitors to this. And so let me go ahead and do that. Let me finish some of this here. Looks like I'm missing a VDD there. And so if I was interested in what capacitors would govern my propagation delay and therefore the clock rate that I can use for a digital circuit, for this transistor up here, I should label my transistors as well. Let me finish this whole picture here. So first of all, like we said last time, it's easy in these digital circuits to go ahead and just tie our sources to our bulks like that. You don't need a special weld to do that for a lot of these things, for each device there. And I guess, let me call this M1, M2, M3, and M4. So these are all MOS devices. The top ones are PMOS devices. And so with all of these, I'm going to have a bunch of capacitors here. So I'm going to have a CGS right here. As my CGS2, I'll have another CGS here associated with device 1. And all of these devices then will have CGSs. 3. And that's a CGS4. I'm going to have my CGDs too. Okay, so I'm basically just writing in all the CGD capacitors that I have. And again, when we look at these capacitors, we're basically saying that for a CGS or a CGD, right, we're saying these are about equal to each other, and they're equal to exactly half of the overlap capacitance of the gate, which is just W over L Cox. Or sorry, W times L times Cox. And this Cox is a Cox double prime. It is a capacitance per unit area. Same Cox that we've been playing with before in our physics discussions. In addition to this, we have CDBs. Right, so we have a CDB capacitance for 2. That's going to go to VDD. We have a CDB capacitance coming out of here for device 1. That goes to ground, and so on and so forth. I guess I'll finish the picture. That one going to ground there. So those are the capacitors we generally worry about, but we've got one more capacitor that will become very important. It actually, these days, overshadows those other capacitors in most instances of circuits, especially for leads going from one function to another, and that is wiring capacitance here. So I'll call this CW. And this is just due to leads, on-chip leads, interconnect, metals that are going from one device to the next. And this capacitance has become so large now because we have so many levels of metallization now. If I had to show the levels of metallization on the left side, there would be 1, 2, 3, 4, more than 8 levels of metallization for a modern CMOS process. And so, this capacitance CW now becomes one of the biggest capacitors here. And so it actually makes analysis easier, but it hurts circuit performance to some extent. The reason why it makes analysis easier, because if you think of, say, any one of these capacitors, say we look at this CDB2 right here, that's a junction capacitor. And so that its equation is going to be something like CDB is going to be equal to a CDB naught divided by, it was 1 plus whatever the voltage was, VDB, I guess I'll call it, divided by some kind of phi factor there, call it phi j there, to the mth power. And so this is just from the physics you saw before here, but what you're seeing is this capacitor depends, right? This thing is a function of that voltage VDB. And VDB is moving all over the place here, right? This output is going all the way from VDD to ground. And so that VDB takes on many different values. So if you needed to analyze this, take into account this capacitor, you would have to take into account the fact that this capacitor is changing as this voltage changes out there. And then the problem gets kind of hairy to a certain extent. But these days, again, you don't really worry about that much anymore because this capacitor here just dominates over these others. Plus the gate capacitors are generally larger than these as well. But anyway, these are the capacitors we're going to have to worry about. When we actually do our analysis, we're just going to lump all these capacitors into one capacitor sticking out here, and that capacitor is going to be about equal to CW, the wiring capacitor there. And the input gate and the gate capacitance of these two devices here, provided, depending on what this looks like. If it's the minimum size type devices, then maybe it's not going to be a big issue. Oh, there's a question. What's the difference between the passivation oxide and the field oxide in the diagram? So the passivation oxide, there's not much of a difference. They're both oxides. The field oxide is there to make sure, and the passivation oxide, you can even say is still part of the field oxide. I'm calling this passivation oxide, but more people will call the oxide that goes on top of this metal passivation. So in other words, there usually is another oxide above all this, and that oxide maybe is more correctly termed the passivation oxide. Some people will call this passivation, some people will call this, some might call both, but in essence, this oxide that I'm showing right here is doing the same thing as the field oxide. And what that's trying to do is trying to separate this metal far away enough from the substrate so that when you put a large enough voltage on this, it does not cause inversion, an inversion charge region there, which could actually short different devices together. Okay, so that's what the field oxide is for in this process. And so, I'm using this word old right here because this is kind of showing an older generation of CMOS. Field oxide doesn't really look this way anymore for the latest generations because this takes a little too much space. Believe it or not, this little amount of space that I'm pointing at right here, where it goes from a large thickness to a small thickness into the transistor, no one likes that because it takes up too much space. Yeah, I mean, they're fighting for every micron that they can get because they're going to want to fit as many devices as possible because area means money. So this field oxide, you'll see this in 143, but in an actual process, you'll do this very differently. You'll do a trench oxide there, or you may not even have a circuit like this. You may have a FinFET, where instead of the transistor looking like this, it's a fin sticking out of the actual substrate there, using almost like a MEMS technology to create that fin. But all these sorts of things you'll learn in 143. So good question, and good, I guess, good encouragement to go and take 143 so you can learn more about this stuff here. This stuff really is cool here. If you like getting your hands dirty and actually making things, 143 is a great class to take, at least when the pandemic is over. I'll say that. Okay, so with that, let's now take a look at a sample circuit that you might make out of these inverters here. And a good circuit to look at is what's called an astable ring oscillator. So I've written here, what is an oscillator? So I think everyone knows what an oscillator is. You're going to know by the time you're done with your lab number 6, because most probably your gain is going to be so high, you're going to get an oscillation. And so an oscillator, when you want to design an oscillator, it's a device that puts out a very stable frequency. Okay, this is a very important device too for almost all electronics. All electronics, I won't say all, there's some asynchronous stuff, but synchronous electronics, it basically uses oscillators. Everything you have uses an oscillator. You know, your wireless communications, you know your digital circuits do, that's what's giving you your frequency. But anything out there that performs to any reasonable level has an oscillator in it. That's why companies that build oscillators, they make good money every year, and especially when they're new technologies. That's where MEMS technology, that's my research basically. A lot of my research has been in MEMS-based oscillators, and I don't know if I should say this, but if you look at some of these MEMS-based oscillator companies, and if you play the stocks, they may be companies you really want to look at these days, because it's MEMS-based oscillators that people are looking at as probably the best option for next generation communication. So 5G, 6G, it's MEMS-based oscillators that people are really paying a lot of attention to right now because of some of their stability characteristics. But so I just said stable, that's the thing. To get anyone can get an oscillator, and you'll find that out from your lab 6. You will get an oscillator. But it's going to be a horrible oscillator. It won't be stable, and you're going to hate it because it's going to prevent you from getting, you know, the results you want for your circuit. So in your lab number 6, what you're trying to do is prevent oscillation. And when you're designing an oscillator, what you're trying to do is make oscillation happen. And the irony of this is that, you know, when you don't want oscillation, it happens. When you want oscillation, it's tough to get. So it's a funny problem to work on, but it's an interesting and cool problem to work on. So this is one instance of an oscillator. It's called a ring oscillator. And you can make a ring oscillator by introducing instability into a digital circuit, in this case by taking 3 inverters that you're seeing right here, and then closing the loop. When you close that loop, you're actually getting positive feedback. And that's what's going to cause the oscillation in your lab 6 too. It's going to be some kind of positive feedback path that you're going to try to eliminate. Should you see the oscillation? Some of you may not see it depending on your design. I guess I'll give some hinters on this. In your design for lab number 6, because I was speaking with someone in office hours today about this, the best performance from a noise perspective and perhaps from an oscillation perspective is probably obtained when you have most of your gain early in the circuit. By early in the circuit, you know, you're going to use 4 transistors. You can think of each of them as being 4 stages in your design. You want your gain up front. Okay, if you can get it in Q1, that'd be great, but you probably don't want to do that because you probably need to use something that can give you a large input resistance. And as we talked about, most high gain transistor circuits probably don't have the best input resistance. But you know, your second stage, I would put the most gain there. Just a hint there if you want to avoid these problems. Maybe I shouldn't have told you that because I'd rather you run into these problems because that's the only way you learn about them. Yeah, maybe I shouldn't have said that. But anyway, I said it. And so that helps you a bit, but you know, try the hookup where you actually get oscillation so you can experience it, right? That's what this course is about. It's about learning, and that's why we have the hands-on thing. We want you to experience the bad so that later on when you see the bad, you'll recognize it and you'll know how to solve it. But anyway, back to this circuit right here. The way that this thing works, now this is an inverter. Say I have a input low applied to this part of the inverter right here. So it starts out with an input low. Well, if that's an input low, then its output you know is going to want to be a high, right? So at this point, you're going to put a high, an H, I'll say there. If that's a high, then this is going to go to a low. If that's a low, this is going to want to go to a high out here, but this is connected to this. And so where this started out a low, this final device now wants to move that to a high. So what happens? It starts out a low, but then it goes to a high. But as it goes to a high, that means this high wants to go to a low. That low wants to go to a high, so on and so forth. That high then wants to go to a low. And you can see how this just continues to oscillate. Each node here is now oscillating from low to high to low to high to low. That's an oscillator now. And with an oscillator, what do you want to do? You want to plot its transient response. So that's what I've got on the next slide here. So I'm going from here to here. And let me first label the nodes before going to that, because the next slide, well, let me go to the next slide and show you where the nodes are. So that's what the waveform is going to look like. And so let me put the nodes in like I was saying. And so this is what I call node 1, node 2, node 3, node 4. And these are the waveforms looking at these, at least 3 of these nodes. So it's node 1, node 2, node 3. And so what you're noticing is happening is that node 1 starts out at an output low. I assume at this point we're transitioning to an output high, so we're to a high input to this. So it's going from low to high. That's this going up right here at node 1. But as that goes up, of course, this output node for this first inverter is going to respond to that. It's going to try to go low. But it's going to take some time to do that. You know that it takes a TPHL now, a propagation delay across this, to actually reach the 50% point where we can now say that this output has gone to a low at that point. And this output, of course, is driving the input to this stage here. And so there's going to be a propagation delay across this inverter number 3 here, that in order to go from this 50% point to that 50% point going up, that's going to take a TPLH3, low to high in this case. Once that hits 50%, of course, this is going back to node 1 at that point. So node 4 is node 1. Let me not call it node 4. Let me call this node 1 here. Okay, so that then goes back to node 1, and it causes this transition. That's going up, and so this transits down. And so what you've seen here is that this is like a square wave coming out of this. And then you're going to have another part of this that's going to have a delay before you see the voltage at the input to the first inverter go back up. There's going to be a certain amount of delay that's going to be dependent also on the high to low propagation delay transition times there. And what we're kind of interested in here is what is the frequency of this oscillator. Like I said, the oscillator, the whole purpose of the oscillator is to put out a stable frequency. And so if we want that ring oscillator stable frequency, we're going to want to determine the period of oscillation. And so as you've learned in different classes, I'm sure, you can define that period here. Let me go to this color. Off of here. So at that 50% point, I'll come up here. And I'll come out to this 50% point out here. Let me come out to that. Oh, got to go straight. So there's my 50. And so this whole thing all the way across here, that's my period. That's the period of oscillation. Of course, 1 over the period equals the frequency. And so that's what I'm trying to determine. So how do I get this period? Well, I have to sum up all of these propagation delays across here. And so if I have the situation, I guess I could say that if I define this time here as, say, T1, and this time as T2, then of course the total period is going to be equal to T1 plus T2. And I can write now an equation for T1 because I have these propagation delays already indicated in this diagram here. So I could say that T1, the time it takes to do that, that's equal to TPLH1 plus TPHL2 plus TPLH3. And that's that period there. And I can also say that the period, not period, but that's that time span there. I could say T2 then is going to be just the opposite of this, right? It's going to be TPHL1 plus TPLH2 plus TPHL3, right? Because it's now going the other way. and trying to get all the way up there. And so each of these devices are making the opposite transition here. And so if I add these two together, that'll give me T, and then frequency is just going to be equal to 1 over T in this case. Right? So this then allows us to get the frequency of this. And so for a special and common case, you'll design this to be symmetric. And so if you design each of these inverters to be identical and symmetric, oops, yikes, let me move that back up. So I'll take the case, whoop, let me stay in that color. Where you have identical and symmetric inverters. And what's meant by symmetric is that the strength of the PMOS is the same as the NMOS. So you size the W over L's. So the PMOS and NMOS have the same drive strength. If you do that, then this thing becomes a little simpler. You could say that my propagation delay, which is the average of these things here, that's just going to be equal to TP, the propagation delay for each stage. That you're going to be able to write that TPLH1 is going to be equal to TPHL2 is going to be equal to TPLH3, and so on and so forth for all of them. They're all going to be equal here, which allows you then to write out that half of your period is going to be equal to N times this propagation delay, where N is the number of inverters you have in this. And that then allows us to write that T is going to be equal to 2 times N times the average propagation delay for each inverter. And so our frequency then, our oscillation frequency, let me call that F naught for oscillation. So your oscillation frequency then is going to be 1 over 2 NTP. And so that now allows us to determine our oscillation frequency. And this is a calculation that if you're doing digital circuits, you'll do again and again and again. Okay, Parth has a question. For the V1 graph, isn't it TPHL since we're going from high to low? V1 graph, TP... Yes, you're right. It should be TPHL. That's correct. So I should fix that. And that means I have to fix it and everything else below too. So this is TPHL1. And yeah, okay. So let me take the time to fix this so this has to be TPHL1. And I guess this one should be opposite here. And even this one, just to be symmetric, I'll do this. Okay, yeah, you're right. Thanks, Parth. Okay, but you get the gist of all of this, right? So you're just looking at the propagation delays across each of these. You have to add 3 of them together. If they're all the same, then you're just taking N times the average propagation delay, and this then gives you your frequency. And I'm looking at this equation, and it's not that clear, so let me... NTP. Okay? And so now what we really want to do is we want to know how to compute this TPLH, TPHL, average T sub P. And so for that, we're going to have to do some detailed analysis here. And we're going to have to consider the physics of the situation, you know, what region of operation each of these transistors are in as you're making a transition. So this is a setup here that I have to determine the propagation delay in a CMOS inverter. So you can see your inverter. The input is going from a low to a high in this case, and a high to a low. At least we'll take a look at that the high to low transition first. So if we're looking at the high to low transition, this is sort of a transient graph of this here. That, we're going from VDD to 0 basically for a CMOS inverter. And as we transit from VDD to 0, we're going to get to a point where we pass a VDD minus VTN point. We're going to get to a point where we hit the midpoint, VDD over 2. And while all of this is happening, what's happening, we're going from a high to a low. So that means we initially have charge on this capacitor. So let me draw that out here. So the circuit that we're really looking at is this one. We have a transistor here that is doing all the driving, which means it is sucking current off of that capacitor. And so effectively we have this circuit. We have our transistor M1, which is pulling current ID off of capacitor CL in this case. And capacitor CL had some charge on it plus Q to start with, and it had a voltage which I'll call V sub C to start with. And as this current is being taken, is being driven by M1, what that's going to do is take Q and take Q to 0. And when Q goes to 0, that voltage goes to 0. Okay, so this is the problem we're looking at here. And we want to know how quickly we can take this capacitor from a charge state where it was once VDD across this capacitor to where it's equal to VDD over 2. Remember, we only have to go to VDD over 2 by definition of the propagation delays. Okay, and to do this, usually at the input to this, you're going to get some transition that's going up where you really measure from the halfway point to out here. But usually in this analysis, you assume that you're putting all the voltage on this. Yes, there is some portion of this. So if I go back here, there is some portion of this right here where the voltage is not quite equal to VDD, and that it's only this portion here where it actually is equal to VDD at that point. But the approximation people usually make is they say instantaneously at this point we're putting VDD on that. Okay, and that actually happens to be the case for some cases, lots of cases, because oftentimes you're driving from a much faster circuit into a slow circuit. And so you will get a much longer response than the actual rise time that you get up here. For this ring oscillator, that's not the case. But for a digital circuit, oftentimes that's what you're doing. So that's why I have this written. VI is equal to VDD right here at T naught, which is where we're actually applying our input signal here. And what we then want to determine is how long it takes to go from VDD down to the halfway point here, which is going to be a time that we're calling T sub 2. And so what we're already indicating here is that during these transitions, M1 is going to be in different regions of operation. So as we go from VDD to VDD minus VTN, we're going to have a situation where we have VDD. So if I go back here, if I have a voltage all the way at VDD, I have no voltage drop across the VGS of M2. So M2 is going to be off. For M1 is going to be saturated throughout this here because it's, M1 is going to be saturated because I've got a lot of voltage across M1. I always have 5 volts across M1. But I have to look at the drain to source voltage of M1. Once that drain source voltage drops to the point where it is VT below this gate voltage, then M1 is going to go to the linear region. So right here, once we reach VDD minus VTN on that output, which is this voltage right here, M1 is going to get out of saturation. It's going to go into linear. And suddenly it has a different drive power. It has a different ability to pull charge off of that capacitor. And we need to account for that if we want to get an accurate answer for what our propagation delay is. Okay, so you can already see some of the complexity of the problem here, unlike analog where we just assumed everything was saturated because we biased it that way. In digital, we've got some things saturated, we've got some things off, we've got some things linear in different regions there. Okay, so with that backdrop, let's go ahead and start to do this analysis. And so what we're going to do is we're first going to determine this time, T0 to T1, while M1 is saturated. Then we're going to determine this time, T1 to T2, while M1 is linear. We're going to add them together, and adding them together is going to give us that propagation delay for a high to low transition for this inverter. Okay, so let's go ahead and start this. All right, so I'll just title this that this is one of our cases. This is the case where V out is greater than or equal to VDD minus the threshold voltage VTN, in which case M1, like we were saying, is saturated. Okay, well, we know the saturation equations from our physics, and so this is where I say all the physics we did, we were also talking about digital circuits while we did that. We're talking about both analog and digital circuits. So we actually have put in a lot of lectures into learning digital circuits. You just didn't know it yet. We're just now applying it to digital circuits right now. So one of the things we got out of our physics is that in saturation, the current that is going through the NMOS device is going to be equal to a what we called 1/2 mu n Cox times W over L of our NMOS device times VGS minus VT. Let me make this the total voltage. VGS minus VTN squared. In digital, though, or in general, it's probably good to be a little bit lazy and not want to keep writing that mu n Cox times W over L. So what we will do is we will call that Kn. Okay, so this, we abbreviate, we just give it a symbol Kn. So that becomes Kn times VGS minus VTN squared. And this now has to be equal to the current going through this capacitor. And so you know that equation for current through a capacitor. That's going to be equal to CL, and I'll put a minus sign there because the current's going out, opposite direction of the polarity of the VC. But that's minus CL times the derivative of that voltage VC with respect to time. Okay, so I have this differential equation. This is a rather simple one to analyze because it just comes down to integration. So I'll pull the dt onto the left side, and this becomes minus, dt is equal to minus 2 times CL times dVC divided by that Kn times VGS minus VTN squared. Okay, taking that one step further here, so actually plugging in the fact that VGS in this case is VDD, so we're assuming that VGS instantaneously goes to VDD, like I said, which is our output high. Let me generalize this and say that this is equal to output high, which in this case is equal to VDD. And that's also equal to our input voltage V sub I. So in this case, I'm going to write that out. I'm going to just write this out as minus 2CL now times dVC divided by Kn times VDD minus VTN squared. Okay? And so if I want the time here, I need to integrate. So I'm going to go ahead and do that. I'm going to integrate from, it's going to have to be from T0 to T1. Only T1 because that's the point where, that's the section in time here when the transistor is saturated. I'm going to have a different analysis for this T1 to T2. And so I'm going to set that equal to integral from, and we're going again from VDD, in this case to VDD minus VTN. That's the range at which that transistor stays saturated of this same equation, minus 2CL dVC divided by Kn VDD minus VTN squared there. And so if you go ahead and do that integral, then you end up with T1 minus T0, that time slice we're looking for, is equal to minus 2 times CL divided by Kn times VDD minus VTN squared times this quantity out here, VDD minus VTN minus VDD. Of course, those two VDDs you could see conveniently cancel out right there. And so I can now write the total equation here for T1 minus T0 as equal to 2CL, and those minus signs sort of cancel each other out to positive there, divided by Kn times VDD minus VTN times a VTN divided by a VDD minus VTN. And the reason why I have written it out this way, instead of turn this squared term into two terms here, is because I can sort of recognize this first term here. This term right here, this 1 over Kn VDD minus VTN, we saw that before. And what that was equal to, I could put 2 times CL, was the on resistance of our transistor when it was in the linear region. And so I actually can write this as 2 times CL times R on times this ratio of voltages, VTN divided by VDD minus VTN. And this now becomes my expression for at least the time it takes to go from VDD to VDD minus VTN, which is the time it takes for the transistor to get out of saturation there. And so in this case, let me just point out, like I said, that R on here is equal to 1 over Kn times VDD minus VTN. If you look back in your notes, when we're looking at linear transistors, this was that linear resistance. This is that resistance you had in that lab where you put that transistor across that op amp. Okay, so this is an effective on resistance. So I'll call this an effective on resistance for this transistor. It looks like a linear region resistance, but remember, it's not really just linear region here. The transistor is kind of in the saturated region here. But because it's transitioning across that, it looks like that linear resistance that we had. So, in effect, at least in this region, you know, looking at that circuit that we're analyzing, we can think of the transistor as behaving like this, as just this R on resistance. And so exactly that circuit we were using before to approximate the transistor, and remember when we were looking at the VTC of the CMOS inverter, you know, we now see that that is a very valid circuit. I can call something an R on here, and that R on is merely equal to the linear resistance of that transistor, even though it's a saturated transistor in this region here. Okay? And so this should make some sense for you too. We're looking for time, and so we really have time. We have capacitance times resistance. That's like a time constant that has units of seconds. We're modifying it by this, and so this tells you that for propagation delay, your supply voltage, your threshold voltages, they make a difference. Right? They're what sort of decides what your delay is going to be, along with the physics that determine this R on. Okay? And so that's the analysis to get at least through the saturation region. However, we still have more to go. We have to get this analysis from T1 to T2. And so we've got another case to look at. And I guess I'll go ahead and move off of this, and so I can leave that other thing on there. And take this second case that we have to deal with. Let me go back to the black ink. And so now we're looking at a case where V out is going to be less than VDD minus VTN. And so in that case, like we said, that's when the NMOS device is going to be linear. That's when the drive device is going to be linear. And so in this case, I have to take the linear region equation for current, so ID linear instead of saturated, and equate that to minus CL times dVc dt. Okay, so if I plug in that linear equation using that K notation, so there's Kn, that's going to look like this. Kn times VGS minus VTN minus VDS over 2, all I'm writing is a linear region equation, times VDS, is going to be equal to minus CL times dVc dt. And so we have to do the same thing. We're going to have to integrate this thing, or at least solve the differential equation that we end up with here, which will end up just being an integration. But let's first plug in some things that we know. We know that VDS, like we used before, that's equal to VC. We know that VGS, which is our input voltage, is equal to VDD. So both of these things together mean that I can write this term on the left here as follows. I could say that this term on the left is going to be equal to Kn times VDD minus VTN. I still have a variable V sub C, so I have to keep that as a V sub C. And that then is going to be equal to minus CL times dVC dt. Okay, so I now have this equation here. And so just to get rid of this over 2 right here, I'm going to multiply through by 2, both sides. So multiply through by 2 both sides, pull the t's on one side, dt on one side, pull the vc's on the other side, and I end up then with the integral equation, integral from t1 to t2 of dt is going to be equal to, well, let's put more than dt there. Let's take some of the constants and move it out there to make the right side a little simpler. So let's pull out the Kn and the 2 times CL and keep those with our dt. And then let that be equal to the integral of all the rest of the stuff. We still have the minus sign there, which I'll put on the outside of the integral. We're going to say this is going to go from V1 to V2, and you know what V1 and V2 are. V1 is going to be VDD minus VTN, V2 VDD over 2. I just don't want to write them much there. I'll write them at the end, though. Of dVC divided by quantity 2 times VDD minus VTN minus V sub C, that whole thing times V sub C. Okay, so we have to take that integral. And to take that integral, you know, you have to go back to your math classes that you've had in the past, your calculus classes. We're basically taking the integral of what? Dx over a minus x times x. And so you can do a partial fraction, you can expand the fraction here. And so we can have the integral of this part plus the integral of dx over ax. Right? So in the end, we have 1 over a times the integral of what this ends up being here. 1 over a minus x plus 1 over x dx. And that whole thing then is going to be equal to 1 over a times the natural log of x over a minus x. Okay, so that's our integral. This is the integration formula that we need to solve that integral on the right side. And so then we're going to plug in what we know as V2. So V2 is VDD over 2. Right? We're not going all the way down to ground. We're going to halfway to measure our propagation delay. V1 is going to be what we started with in this region, which is VDD minus VTN. That's the point where the transistor went from saturation to linear. And so using this then gives me, solving that integral, gives me Kn over 2 times CL times T2 minus T1 is going to be equal to minus 1 over 2 times VDD minus VTN. Let me make that clear. Times the natural log now of my x, which was V sub c, divided by 2 times quantity VDD minus VTN minus V sub c. And I'm going to have to evaluate that between my limits of integration, VDD over 2 and VDD minus VTN. And there's some algebra involved here, which I'll let you do. But after you do all this algebra, you end up then with minus 1 over 2 times VDD minus VTN times the natural log of VDD divided by 4 times VDD minus 4 times VTN minus VDD. Here at the bottom, obviously there's more simplification that can go on here. So this then allows me to write then T1 minus T2, or T2 minus T1, moving the Kn and Cl on the other side here as Cl. I may not be giving myself enough room there. Let me pull this down a little bit. Times a familiar term now that you're seeing. Now you see this Kn together with VDD minus VTN again. That's that resistance value. That's R on again. But then times natural log of, and shifting things around, doing some simplification here, 4 times VDD minus VTN minus VDD over VDD, where I basically took the minus sign out of this here in order to get that. And I can then write this as this CL over Kn times VDD minus VTN times natural log of 4 times VDD minus VTN. I'm just moving to get this in a certain form for you. Divided by VDD minus 1. And so that ends up being our equation for T2 minus T1. I can kind of single this out here. And so if I wanted the total propagation delay for my high to low transition, I would have to add this with what I have on that side, which I guess I'll go ahead and do here. I have no space there, but now let me move this thing here and just write it out here. So in the end, TPHL, which is what we were going for, that is going to be equal to this T2 minus T1 plus T1 minus T naught, which of course equals T2 minus T naught, which is TPHL. That then, if I take advantage of the fact that we recognize that this 1 over Kn, VDD, VTN, these things that you have there, that is R on. For both of these things we have R on, so we end up with R on times CL times the natural log of what we just wrote, 4 times VDD minus VTN divided by VDD, so some ratio of voltages, minus 1, and then plus 2 times VTN over VDD minus VTN, and that quantity closed there, that equals TPHL, where, to be complete, the R on resistance was 1 over Kn times VDD minus VTN, which is just like the linear resistance of that that we had seen before for a linear MOS transistor. And so this then ends up being our TPHL. Okay, it was pretty hairy to get this whole thing, but we got it. Took some integrations. It just took a bit of math to get to this TPHL equation. So this is a TPHL equation for a long channel device. Well, for long channel devices, I should say. The equation changes a bit when your devices go to short channel. So what do I mean by short channel? That's not something we've discussed much in this class. That's something you will learn more about if you take ee130 and ee230B, because these days the transistors are so small that their physics changes a bit, especially for digital circuits, to the point where the actual current equation is no longer that much of a square law. It now looks a little more linear with the gate voltage. but that's just letting you know. But for now, for our purposes here, this is a classic equation that you can use to calculate TPHL for this. And one thing you can see out of this thing here is that, just an observation you can make, TPHL, that's equal to this R on times CL, right, times some kind of modifying factor. And that modifying factor is some function of your VDDs and your VTNs there. Okay? And so there it is. There's your propagation delay from high to low. We can do a similar thing in going from low to high. We're not going to go through that whole process. It's exactly the same process, but using opposite devices and that sort of thing in the opposite direction. And so, I guess what I'll do is just write in what that is, as far as an expression is concerned. And maybe I can do that next time. Well, no. See, next time what I want to do is go a little bit back to analog, so I could show you some stuff that goes into 140. So I'm going to go ahead and finish this up right here and say that if we wanted to go from if we wanted to get TPLH, it's the same analysis, right? So this is the thing where right now where the output goes low to high. And so in this case, what we're really doing is connecting the capacitance to VDD and charging up that capacitance through VDD. In this case, it's the PMOS that does the work. The PMOS is on. The NMOS is off. So pictorially, if this is VDD, then it's this transistor, the PMOS transistor up above, that has V sub I on it, now equal to 0 volts. It is the only thing attached to this capacitor because the NMOS device is off in this case. And what it's going to do is it's going to shove current into that capacitor to take the capacitor voltage, which is the same as V out in this case, from 0 volts to VDD. Okay, and so you're basically charging up that capacitor with a plus Q that's coming from charge from VDD because you've just closed this switch here. And so through a similar analysis, I can get the expression for the propagation delay, and I'm not going to do that analysis, I'm just going to write it. So I'm just going to say now, through a similar analysis, we get TPLH, the low to high transition, is going to be that on resistance times CL. Now these are for the PMOS device, the on resistance, times natural log of 4 times VDD minus absolute value of the PMOS threshold voltage, which is a negative number, divided by VDD minus 1 plus 2 times the absolute value of the PMOS threshold voltage divided by VDD minus the absolute value of the PMOS threshold voltage, close parentheses. That then is the TPLH. And then finally, maybe what we're looking for is the propagation delay, the average propagation delay. That's going to be TPLH plus TPHL divided by 2. Okay, so those are all the equations you need to determine the propagation delay of a CMOS inverter, which is probably one of the most important calculations people will make, because that will then tell you how fast your clock can be in a given digital circuit. Okay, so with that, I guess we'll end this lecture, and we'll continue talking about this, maybe more complex gates in the next time, but I also want to get to at least showing you a differential pair, because that will prepare you a bit for 140 if you want to take that. So that's it for today. I will see you on Friday.